So in this system of equations, since everything's in standardized format, we've got something x plus something y equals something. The idea is we don't really need the variables listed out. We can just treat this equation as 3, 3, 9. That has all the important information. We don't really care about the names of the variables. We're just using position to keep track of which number is multiplied by which variable. And then the next equation, 4, negative 5, 2. And the last equation, negative 7, 29, 19. So this matrix has all the information from the system of equations. We're just presenting it in a different format. We also usually draw a vertical bar here to separate the coefficients of the variables and the numbers on the other side of the equation. So if you look at this in terms of rows, each row represents one of those equations. If you look at it in terms of columns, each column represents coefficients of a different variable. Here's all the coefficients of x. This column is all the coefficients of y. And this column is all the numbers on the other side of the equation. And of course, you want to put it in this standardized format first. Something x plus something y equals something, or however many variables you've got. Any questions on that setup so far? And this is usually called an augmented matrix. Augmented just means with something else attached to it or something else added onto it. The idea of augmenting is we've got this matrix of coefficients and we've augmented one extra column. We've attached one extra column to it. So that's usually what we mean by augmented matrix, a matrix that has had an extra column or columns attached onto the end. And what we're going to do is we're going to do some row operations. Row operations are using some rows to influence other rows or modifying rows in certain very specific ways. And these ways ultimately correspond to the way we'd be solving this using elimination methods from previous math classes anyway. One example, for instance, what do you notice about all the coefficients in this equation?
They're all multiples of 3.
Right. So how could we simplify that equation quite a bit?
Divide by 3.
Yeah, we could just take 3x plus 3y equals 9 and divide both sides by 3. And we'd end up with an equivalent equation, x plus y equals 3. And we can do the same sort of thing in matrix format. The equivalent of this would be multiplying or dividing everything in an entire row by some constant. So we can do that here. Let's say we call this multiplying the first row by 1/3. Or you could say dividing by 3, but it's usually just for consistency, we usually write it as multiplication. So we're multiplying the top row by 1/3. And let's see what we get. We get 3, 3, 9 becomes 1, 1, 3. And then the other rows, and I would usually check all the rows to see if there's some easy integer you can divide out. And of course, these don't even have to be whole numbers, but it's usually easier to work with if they are. And then continuing from there, one of the other things we often do with systems of equations is combine equations by, for instance, adding an equation to another equation, or adding a multiple of an equation to another equation. And to do that, for instance, let's say we wanted to use these equations to cancel out the x's entirely. You could multiply, and remember we now have this as 1, 1, 3 instead. Let me fill that in. What could we multiply this equation by that would allow it to cancel out the 4x here?
-4.
Right. So we could multiply this equation, both sides, by -4 and add that to this equation. So 4x plus -4x, -5y plus a -4y, 2 plus 3 times -4. But we can do that in row form also. The way we would write this is we take row 2 and we're going to modify row 2 by adding -4 times row 1. And there are different notations for writing this. I usually just write it as whatever row you're modifying. Next to it, I would write plus some multiplier times the other row you're using to modify it. And you could use any row to modify any other row. For consistency, it's often a good idea to sort of work from top to bottom. Use the top row to modify the rows underneath it, and then use the second row to modify the row below that, and so on. So let's see what this turns into. Top row, we're not changing, so that's still 113. Second row, we've got 4, and we're adding -4 times 1. So 4 plus -4 times 1 is going to be 0. And then -5, what are we going to add to that?
-4.
Yeah, -5 plus 1 times -4, so that'll be -9. And then what are we adding to the 2 here?
-12.
Yeah, 2 plus 3 times -4 would be -12, so 2 plus -12, -10. So this is our new second row. Any questions on that so far? And while we're at it, we can also this is really kind of a separate step, but we can sort of combine them into one step. We also want to modify row 3. Because going back to the previous math classes approach, like high school algebra, for instance, you'd want to use a pair of equations to cancel out x, and also maybe use another pair of equations to cancel out x as well. We can do that in essentially the same step. We can use this 1 to eliminate this -7. What multiple of 1 would cancel out a -7?
7.
Yeah, so we can modify the third row by adding 7 times the first row. And let's see what we get there. -7 plus 7 times 1, that's 0, because we want that to cancel out. 29 plus 7 times 1, 29 plus 7, so that'll be 36. And then 19 plus 21 would be 40. Any questions on that so far? And I want to point out a very useful thing we have just accomplished here. If you take a look at this 1 is now alone in its column. We've gotten rid of everything else below it. This number here is usually called a pivot. The pivot is defined as the first non-zero you encounter as you go from left to right in a row. The first non-zero number in a row from left to right. So for instance, in the second row, the pivot would be the -9, because that's the first non-zero you encounter. In the third row, the pivot would be the 36. The idea is you can use the pivots you can almost think of the pivots as tools you can use to get rid of everything else. So from the first row, we found the pivot was a 1. We used that pivot, that 1, to eliminate everything below it. Next, we can use the next pivot, this -9 here, to eliminate everything, ideally everything above and below, and see what we get. So let's try that. And I want to emphasize you could do this in any order. There's no reason that you have to go from top to bottom, left to right, but it's usually much more convenient to do this in an organized sort of fashion. And this is the usual conventional way to do that. Start with the top row, find the pivot, use that pivot to eliminate everything under it. Then take a look at the next row. The pivot should be at least 1 space further over because you caused a 0 there. Use that to eliminate everything above and below. So for instance, how would you use this -9 to cancel out this 1?
Multiply it by a 9.
Yeah. And of course, we'll have to do this with the entire row. So we're going to modify row 1 by adding 1/9 of row 2. And while we're at it, we may as well also modify row 3 by adding what multiple of -9 will cancel out the 36?
4.
So we'll add 4 times row 2 to modify row 3. And let's see what that becomes. So we've got a 1. We're adding 1/9 of 0, so no change. This is one of the really nice things about doing this in this organized way and establishing some zeros. Once you've established zeros in a column, other than the pivot, of course, those zeros guarantee they won't mess around with anything in that column. So this column is not going to change any further. We've locked it in place. So 1 plus nothing, 1 plus -1 cancels out. And then 3 plus -10/9. So we could think of that as 27/9 minus 10/9, so 17/9. Next row, we're not changing it this time. And then third row, we're modifying by adding 4 times the second row. So 0 plus 4 times 0 is still 0. 36 plus -9 times 4 is 0. And 40 plus -10 times 4 is also 0. And that tells us a very useful piece of information. If we've got this row that's all zeros, 0, 0, 0, what would that row look like as an equation? If we go back to the idea that remember, each one of these rows represented an equation in the first place. If you rewrite this final row as an equation, what would that equation be?
0x plus 0y equals 0.
Yeah. And that's very convenient because 0x plus 0y equals 0 is true. So this row, at least, it doesn't really tell us what the answer is, but it at least doesn't contradict the idea of an answer. On the other hand, if we had gotten something that wasn't 0 here, like let's say this had turned into 0, 0, 5. If you get an equation 0x plus 0y equals 5, that means there's no solution at all. There are no x and y values that make 0 plus 0 equal to 5. So keep watch for that. If the final row ends up being 0, 0, 0, 0, 0, and then on the other side something that's not 0, that immediately tells you this system of equations has no solution. On the other hand, if you get a row of all zeros, that doesn't necessarily mean there is a solution, but it at least means the final row does not provide any restrictions. The final row being all zeros says, I don't care what the answer is. The answer could be anything. Final row is just no longer putting any restrictions on what the answer could be. So we look to the other rows. And the first row here, if we write this first row as an equation, what does that turn into?
X equals 17/9.
Yeah, so that tells us the value of x in the solution, if there is a solution, which it looks like there is, because none of these other rows provide any contradictions. And there's one other thing we can do with this row, the 0, -9, -10. Ideally, we'd like to turn this -9 into what?
A 1.
Yeah, and we can accomplish that if we back up a step. Let's say we just take this entire row, and instead of adding or subtracting, let's just multiply this entire row by -1/9. That way the -9 turns into 1. The -10 turns into 10/9, and 0 is still 0. And now what would this equation look like, or this row look like as an equation?
Y equals 10/9.
Yeah. So it looks like we now have a solution. We have one value for x, one value for y, and no further restrictions. And of course, we can check this by plugging both of these values into all 3 of the original equations and make sure they all become true. Because that's really what we want. We want a set of values, a single set of values for all the variables that makes all the equations true. Any questions on that so far?
So would this translate to it intersecting in just a single point?
Yes, the fact that we found one single value for x and one single value for y that makes all 3 equations true means that one point is on all 3 of those lines. So all 3 lines come together at that one point.
What would it look like if it turned out that all of the lines were like parallel or overlapped with each other?
Like if they're all really the same line?
Yeah.
In a case like that, you'd end up with, I think you'd end up with another row of all zeros and then one equation with 2 variables. Because if all the rows cancel out except you have one row with numbers here and here, like let's say your final result was just like, let's say 1, 1, 3, and then 0, 0, 0, 0, 0, 0. If you just have 1, 1, 3 and everything else is zeros, that tells you that x plus y has to equal 3, but it doesn't give you any further information. So that doesn't narrow it down to one set of values. It just tells you how X and Y have to be related to each other.
And that would just be the equation of the line that they would all fall onto, essentially.
Right. And what that would ultimately mean, if you go back to the original system of equations, if you get just like 1, 1, 3, and everything else is 0, that ultimately means that all three of these equations were really the same line, just written in different formats. Like maybe if you had 1, 1, 3, and 3, 3, 9, and 10, 10, 30. Just disguised by multipliers, but ultimately the same line. So that would mean that they're all really the same equation, just written in slightly different formats. Any other questions on that so far? And one other thing I'd like to emphasize here, our end goal here, what we were really striving for, going back to the idea of pivots, what do you notice about the pivots in the final format we settled on?
They're diagonal.
They're diagonal, and they don't necessarily have to be diagonal. They could be in a slightly different arrangement. But yeah, they're ones. And also, what do you notice about everything else in the columns?
Everything else has been canceled out.
Right. This is really the goal we're generally trying to shoot for. If you're trying to solve a system of equations using this augmented matrix row reduction method, the goal is to get every pivot alone in its column, so everything else in the column is 0, and also every pivot to be a 1. And turning them into ones is fine to do as a very last step, like this -9 turning into 1 just by multiplying that row by -1/9. But this is really the goal. Every pivot should be alone in its column. Every pivot should eventually be the number 1. And also you want them to have them in order from top left to bottom right. They don't necessarily have to be on the main diagonal. You might skip a column or something depending on how the numbers work out. But you want them to be in order from top left to bottom right just for consistency. And this is usually called reduced row echelon format. Or RREF. So when you see a matrix being described as being in RREF, or row reduced echelon format, that means that every pivot is a 1. The pivots are all alone in their columns, everything else reduced to 0, and in order from top left to bottom right. And this is usually the most convenient format for, like for instance, in this case, we can just read the answers directly off of this column. Or even if there isn't one unique solution, maybe there's many solutions, row reduced echelon format allows you to write out those many solutions in a much more organized way. Excuse me. Any other questions on that? All right. I would also like to mention one more thing about this original system of equations. If we go back to the original matrix that we were using to represent it before we did the operations here. Going back to 339. If we look at this in terms of the rows, we can say each row represents a line on the graph, and we're looking for the point where they intersect. But we could also look at this in terms of the columns. If you look at this as 3, 4, and -7 all being multiplied by x, you could think of that as a 3×1 vector multiplied by some number x, and then the coefficients of y, 3, -5, 29, being multiplied by some unknown scalar y. Added together. And what do we call that, by the way? If you've got a vector times a scalar plus another vector times a scalar, what's the usual term for that?
Linear combination?
Yeah, this is a linear combination of those two column vectors. And we want those to add up to these numbers, 9, 2, 19. So an alternative way you could think about this system of equations, instead of thinking of it as 3 equations or 3 lines and you're trying to find where they meet, you could think of this as 2 vectors, and you want to find out what linear combination of those 2 vectors makes this new vector. What do you have to multiply by 3, 4, -7, plus what do you have to multiply by 3, -5, 29 to make it add up to 9, 2, 19? And we found those coefficients. It turns out if you take 17/9 times this first vector plus 10 ninths times the second vector, you get exactly this new vector. So the textbook usually calls this the column picture, or column way to visualize the system of equations. You can think of that as the row picture being each row represents an equation. You're trying to find where the graphs of those equations intersect. Or the column picture, if you think of the columns as vectors, and you're trying to figure out what multiples of those vectors can you add together to get this new target vector. Like how many copies of one vector plus how many copies of the other vector add up to the result you want. And we found that you have to add 17 ninths times one vector plus 10 ninths times the other vector to get there. So it's often useful to be able to look at the same problem in multiple different ways. This is essentially two different ways of looking at the same overall matrix problem, two different ways of visualizing the setup and the results. So if you look in the textbook for row picture and column picture, that's what that's talking about. Any other questions on that? Or anything else you'd like to work on?
My professor left off class the other day and kind of just like threw the Schwartz inequality out there without a whole bunch of explanation.
Okay. Is that the one with the dot product?
Yeah, it's the like absolute value of the dot product of two vectors has to be less than or equal to the dot product of their two what's it called, lengths or magnitudes.
Yeah, the magnitudes. And if you take some vector u and some vector v, any two vectors, and take their dot product, the size of that dot product as an absolute value, because dot product could be positive or negative. So let's say we take an absolute value. It can't be greater than magnitude times magnitude. It could be equal to, but it can't be greater than. It's less than or equal to. So this is basically putting restrictions on how big a dot product can be. The dot product can be as big as magnitude times magnitude, or it could be smaller than magnitude times magnitude, but it can't be bigger than magnitude times magnitude. And this ties into another formula you may have seen for dot product in other classes. Have you seen how the dot product actually relates to the magnitudes?
With the cosine?
Yeah. U dot v always ends up equaling magnitude of u times magnitude of v times the cosine of the angle between them. And what's the largest cosine can be?
1.
Right. So if cosine is 1, because if the angle would be 0, for instance, then u dot v is just magnitude u times magnitude v. That's the or equal to part. Or cosine theta could be smaller than 1, which would be the less than part.
Okay.
So the Schwartz inequality is basically just the result of this describing the size or the restrictions on the size.
Okay, yeah, that makes more sense.
Any other questions on that? And this can also be proved more geometric, or I guess more algebraically, because the magnitudes are also defined in terms of dot products. Formally, magnitude is defined as the dot product of u and itself in the square root. U dot itself would be magnitude of u squared. So magnitude of u is defined as the square root of u dot itself. So you can always rewrite magnitude as this square root of a dot product with itself. So we're basically just saying that when you take the dot product of u and v, it's less than or equal to square root of u dot itself times square root of v dot itself. And you can prove this algebraically. It's fairly straightforward, just kind of tedious to write out by writing out for any size vector. Like let's say you've got 2 by 2 vectors. If you have like A, B, and C, D. You can write that out as just A times C plus B times D. And likewise, you could write each of these out, A squared plus B squared in the square root, and then C squared plus D squared in the square root. And you can actually write out each of those and expand it and simplify and show that this one cannot be more than this one, because this one ends up having some extra terms. And worst case scenario, those extra terms cancel out and these end up being equal. But if those extra terms do not cancel out, then this side is larger. But that's algebraically the reason why that works the way it does. So Schwarz inequality is basically just a fancy way of describing this limitation, this restriction on how big a dot product can be. And also going back to the idea of cosine, what sort of angle leads to cosine being the largest?
Zero?
Yeah. In other words, when the two vectors are in the same direction as each other. So because the angle between them, if that shrinks to zero, they're in the same direction. So the dot product is largest when u and v are in the same direction. And when would this cosine be zero? What angle causes cosine of the angle to be zero?
90.
Right. So that means the dot product is zero when the vectors are perpendicular to each other. Also, what would lead to cosine being the lowest it could possibly be? How would you get a cosine that's less than zero?
Oh, take the negative, so like either negative 90 or 270 degrees.
Not in this case. If you go to negative 90, cosine of negative 90 is still positive, or still zero, I mean. Because if you look at the graph of cosine, it's highest at 0 degrees, drops to 0 at 90 degrees, and also drops to 0 at negative 90 degrees. But if you keep going, when is it going to hit -1?
180 degrees.
Right. So that means if the vectors are 180 degrees offset from each other, exact opposite directions, then that means u dot v is going to be the lowest possible negative. So it's the lowest negative, I guess I should specify largest positive when they're in the same direction, lowest negative when they're in exact opposite directions. So if you've got vectors in exact opposite directions, the dot product will be negative and as low as possible. If they're in exactly the same direction, the dot product will be positive and as large as possible. And then if they're perpendicular, dot product will be zero.
So when you say lowest number, do you mean they're essentially like canceling each other out so they're almost at zero, but not quite?
Lowest in the sense of most negative, farthest from zero, but in the negative direction.
Okay.
You're going to get a dot product being zero when they're perpendicular. If they're close to perpendicular, like let's say you've got vectors that are an angle that's a little bit bigger than 90 degrees. Since that's more than 90 degrees, it's closer to the opposite directions version than the same direction version. So this would result in the dot product being negative, but pretty close to zero. The closer they get to opposite directions, the more negative it becomes. Likewise, if they're in exactly the same direction, you get a large positive dot product. If they're a little bit offset, you get a slightly smaller positive value, and smaller, approaching zero when they're perpendicular. So you'll only get perfectly zero if they really are perpendicular. If it's almost perpendicular, you'll get close to zero, but not quite. And the further you get from perpendicular, the further the dot product gets from zero. So this is a very convenient way to test if vectors are perpendicular. If you have two vectors listed in terms of their coordinates, take the dot product. If the result is zero, then you know the vectors are perpendicular. If the result is positive, then you know the angle between them is acute. If it's negative, you know the angle between them is obtuse. And of course, if it's zero, you know they're perpendicular. And this also works in reverse. If you have two vectors where you don't know the coordinates, but you want them to be perpendicular, you can write out the vectors in terms of variables, take the dot product and set it equal to zero. And then maybe you can solve for one of the variables in terms of the others and get some information about what has to be true to make them perpendicular. Any other questions on the dot product stuff? Or anything else you'd like to work on?
I actually had a question back on like the matrix stuff. Sorry, I was in the library, so I couldn't talk earlier.
Mhm.
But so what would you do though if you were given like two vectors and asked to find the linear combination? Because then like I guess the third column isn't really there.
Is it just saying like find any linear combination of these two vectors?
Yeah, like if it's like a line or plane, or if it can be like anywhere.
Okay, so we're in that case, that suggests we're looking for all possible linear combinations and trying to figure out, do they create vectors on just a line or vectors on a plane?
Yeah.
So for that, let's try out some examples here. If you have, for instance, let's say this vector, let's call this vector A, and the vector B. So with these two vectors, if you're looking at linear combinations of them, what do we mean algebraically by a linear combination?
It's like the same vector multiplied by like another number, like by 3 or 2.
Yeah, so we're taking vector A and multiplying it by some scalar, some number. Let's say we call this C1. And we're also taking vector B, and we're also multiplying that by some scalar. Let's call this C2. And if we want to see where we can get to from that geometrically, let's say, ignoring B for now, if you just take vector A and multiply by a scalar, what would that do to vector A? Like for instance, if you just multiply vector A by 5, what would happen to it?
Sorry, you froze for me, so I didn't get that part.
Oh, if you just take vector A, so ignoring vector B for now, if you just take vector A and multiply by, let's say, by 5, what would happen to it?
It would get bigger by 5.
Right. Gets larger by a factor of 5, but it does not change direction. It just gets longer. Or if you multiply by something less than 1, you could shrink it. Maybe you multiply by 1/3 and it becomes a third as long. Or what would happen if you multiply it by a negative value?
Would it reverse it? I'm not sure.
Yeah, if you multiply A by, let's say, -2, it would become twice as long in the exact opposite direction. So by multiplying A times any scalar, you could get to anywhere along this entire line. You could make it as long or as short as you want, and also in the exact opposite direction as long or as short as you want. So if you're just looking at one vector and all possible scalar multipliers, in other words, all linear combinations of just this one vector, that forms an infinite straight line, because you could get to anywhere on that straight line using scalar multipliers. Same thing with B. If you multiply B by any positive scalar, you'll just make it longer or shorter. If you multiply by a negative scalar, you'll reverse the direction. So this blue line represents all possible linear combinations of just A alone. In other words, all multiples of it. And this purple line represents all possible linear combinations of just B alone. But if we want linear combinations of A and B, that means we can multiply each one by a scalar and we can add the results together. So for example, you might go some distance along the A line. Maybe you go A times 1.5. And you get to here. But then we're adding vectors. Adding vectors, you go some distance in the A direction, and then from there as your new starting point, go some distance in the B direction. So maybe you got 1.5 A plus 2/3 of B. So 1.5 A means go that far in this direction. 2/3 B means go this far in that direction. I guess that should be more parallel. Oh, it's not right. And so you end up there. So if you've got 1.5 A plus 2/3 B, just as one example, your result is this vector. Or if you think of it in terms of a point, because you could think of a vector as the path, the straight line path from the origin to some location, or you could think of the vector as just representing that final location. So this location, or to put it another way, this vector is one example of a linear combination of A and B, because that's a location you can get to by going some distance in the A direction, and then from there going some distance in the B direction. Any questions on that so far?
No, the picture is really helpful though.
Yeah, it's very, I mean, a lot of this is typically presented as more of an abstract algebra thing, but I think it's a lot more easy to understand if you see the geometry behind it as well. Because this whole thing was established to deal with geometrical stuff in the first place anyway, and using geometry to analyze data. So where else could we get to by linear combinations of A and B here? Like, could we get to this location, for instance?
I would say yes, but you would have to use different scalars.
Yeah, definitely we can use different scalars, but we're still using these same two vectors. So you could go, for instance, some distance in the B direction, as long as we choose the exact right distance in the B direction, and then some distance in the negative A direction, because negatives still work. So we're going some distance along the B direction and then some distance in the negative A direction. And we get to this location. So that's maybe, that looks like 1 1/3 times B. So maybe 1 1/3 B plus, and maybe -1/2 A. And I'm just eyeballing the numbers here, but it's something like that. So this is another location we can get to as a linear combination of A and B. And if you look at all possible locations you can get to, using any numbers you want for C1 and C2, whole numbers, fractions, irrationals, whatever, where else could you get to? If we wanted to describe the set of all locations you can get to by this method.
I'm not sure.
Or to put it another way, is there anywhere we couldn't get to? Are there any limits to this?
I don't think so, because you could put any number, maybe.
Yeah, you can go any distance you want in this direction, any distance you want in this direction. I guess the only places you couldn't get to are places outside the marker board itself. Like there's no way you can get to this location right here just by going this way and this way, because these vectors don't provide any third dimension capability. But since we have linear combinations of these two different vectors, we can get to anywhere in a two-dimensional space. In fact, this is ultimately why we would call this plane two-dimensional, because we only need two vectors to span the entire space to get to anywhere in this region. So I would say that given these two vectors, their span, that is the set of all possible linear combinations, is a two-dimensional plane. And generally, anytime you've got two vectors, their span, that is the set of all possible linear combinations, should be a plane, except, separate this off. What if we had vector A like this? Can you think of a vector B that wouldn't add any new information, that wouldn't allow us to leave this line?
Like if it was the same vector but shorter or something.
Yeah, if B was the same direction, just maybe different size. So if we go back to the idea of starting with A alone, A on its own spans this line. But if you add in B, B does not add any new information. B is just a repetition of the information we already have. It doesn't give us a new direction we can travel in. So that means if the two vectors are parallel, then their span will just be a line anyway. And you can extend this to more vectors as well. If you've got, for instance, three vectors, let's say this vector, and this vector. These three vectors will span a three-dimensional space, because you can go as far as you want in this direction, as far as you want in this direction, as far as you want in this direction. That creates 3 dimensions. But let's say you've got these two vectors. Those so far would form a plane. If you add in a third vector that's part of the plane you already have, you're not adding any new information. So the third vector does not give you a third direction to travel in if the third vector is part of the plane you've already got. So geometrically, that's what you want to look for. does each vector really add new information? Does it really add a new direction to travel that you couldn't already travel in? If so, if every vector really does provide unique new information, then the number of vectors you have determines the dimension of the space you're talking about. 2 vectors form a 2-dimensional space, 3 vectors form a 3-dimensional space, so on. Mathematically, you could even go to 4 dimensions, 5 dimensions, 6 dimensions. It's just not as easy to visualize. But if you've got some repetition, some redundancy, if vector B doesn't really provide any new information that vector A didn't already have, then that doesn't increase the dimensionality. These 2 non-independent vectors, these 2 dependent vectors, still only span a 1-dimensional space. And this gets into the idea of linear independence. In this case, we would say A and B are linearly independent. They provide unique information that doesn't just duplicate what you already have. But here we would say A and B are linearly dependent. B is just duplicating information that we already got from A. So we don't really need both of them. Any other questions on that?
So when you're dealing with vectors that would be linearly dependent to each other, you could essentially use a linear combination to, like, if you have 3 vectors, to combine 2 of the vectors to, like, essentially get you to the 3rd point.
Yeah, one way to look at it, like you said, if you have 3 vectors, if 2 of them can be used to build the 3rd one as a linear combination, that means you didn't really need the 3rd one. So they would be linearly dependent. Formally, it's defined in terms of, can you use a linear combination of these to create 0? Can you get them to all cancel out? But in practice, that usually means that some combination of some of them can be used to build the other one. So you didn't really need that other one. Any other questions on that? All right, I gotta go get ready for my next workshop. So I will see you next time.
Thank you.
You're welcome.